In this module, we'll provide techniques for solving the aircraft equations of motion. In our analysis of static stability, we were only concerned with creating initial restoring moments to counteract angle of attack and sideslip disturbances. But to fully understand the dynamic behavior of an aircraft, we need to analyze the dynamic response of the aircraft to these disturbances over time. And for that, we need to solve the equations of motion. In the diagram, all three responses have positive static stability. However, over time, they differ. Our design goal should be like the yellow response, positive dynamic stability. That being said, there are FAA certified aircraft with negative dynamic stability in some modes, particularly the phugoid mode. Let's quickly review the various versions of the equations of motion. Remember, equations of motion relate the applied forces and moments on the aircraft to the resulting response of the aircraft, and they're derived from Newton's second law. The translation version gives us 3 equations, and the rotation version gives us 3 equations. So in total, we get 6 equations of motion. The first version produced nonlinear equations with forces and moments on the left-hand side. We then manipulated that version to produce an alternate nonlinear version with accelerations on the left-hand side. The third version used small disturbance theory around steady, wings level, and trimmed flight. We then realized we can't measure downward or sideways velocity, so we related those terms to angle of attack and side slip. And finally, we developed a version with non-dimensional derivatives. Here's the first version. They're nonlinear, all the forces and moments are on the left-hand side, but they're coupled. And X, Y, Z, L, M, N are the forces and moments generated by aerodynamics and propulsion. These equations are a function of motion variables, control surface deflections, and thrust settings. So this is what we get after applying Newton's second law. Unfortunately, this version is not very usable. We take that first version and then just rearrange terms and put the accelerations on the left-hand side. So we get u dot, v dot, and w dot on the left-hand side for the translational equations, and we get p dot, q dot, and r dot on the left-hand side for the rotational set of equations. But still, nonlinear, coupled, not very usable. Here's the third version where we linearized the equations by applying the small disturbance theory around steady, wings level, trim flight. So while translation and rotation works for physicists, airplane people prefer longitudinal and lateral directional. So we can just take these 6 equations and reorder them. Now we have them in terms of longitudinal and lateral directional. The longitudinal equations involve motion in the x body and z body plane, or rotation about the y body plane. The lateral directional equations involve sideways motion along with rolling and yawing, which are often coupled. Here's the fourth version where we took those linearized equations but then resolved v and w, side velocity and downward velocity, in terms of angle of attack alpha and side slip beta. So same basic equations, but now involving things that we can measure in flight. This fourth set of equations is often where we start, and where we'll start for most of this lecture. Here's the fifth and final version of the equations of motion, where we basically used non-dimensional stability derivatives. So either the fourth version or the fifth version are often what you'll see in textbooks and on the job. So let's start with the fourth version of just the longitudinal equations of motion. We see that we get three equations, but really driven by four state variables or output variables plus the two inputs. So not very useful. So we really need a more simplified version of the equations. We can get that with the following assumptions. First, let's just assume that the thrust is constant, so we'll get rid of all the delta t terms. Pitch rate really has a minimal effect on z-force, so zq can be 0. That goes away. Angle of attack rate also has minimal effect on the z-force, or really the pitching moment. So z alpha dot or m alpha dot are 0, and those go away. And then if our initial pitch angle is small, so theta naught is approximately 0, we can get rid of a lot of the trig with our small angle assumptions. So cosine of theta naught is going to be 1, and sine theta naught is just going to be theta naught in radians. And then if our wings are level, then the pitch rate is basically theta dot, and then you also get the derivative of pitch rate is theta double dot. Using all these assumptions, we now get three equations driven by three state variables plus only one input. So this is a more simplified version of the longitudinal equations of motion. The equations of motion are differential equations, and so we have to solve them. And there's three techniques: analytically using math, or two, we can use Laplace Transforms, or three, we can use numerical integration. So for differential equations, in terms of analytical solutions, let's focus on first order differential equations and second order differential equations. And there's two traditional forms shown. The first order is x dot plus ax equals f of t, and the second order differential equation is x double dot plus 2 zeta omega n x dot plus omega n squared x equals g of t. Let's face it, differential equations are difficult for most engineers to understand. My tip is go find a friend in the math department when you're looking at a differential equation, because it's tough. You have to determine a number of things. You have to figure out what's the independent variable, what's the dependent variable. You have to figure out the order, whether it's ordinary, homogeneous, the degree, if it's linear. All these things are tough and often require a second set of eyes just to figure out what the answers to those are. And then you have to figure out the solution. The mathematicians like the homogeneous and the particular solution, but the airplane people really want to know what the transient versus the steady state solution are. Now we'll walk through the first order differential equation that we showed before. Any first order differential equation needs one boundary condition to solve it. But our general form is x dot plus ax equals f of t. We find that we get a stable solution if the value of a, the coefficient in front of x, is positive. And for this example, I'm using x dot. So we have x dot plus 2, so that a is positive. And that results in a stable solution. The solution is 5 times the quantity 1 minus e to the minus 2t. And you can see in the plot that the solution does not grow without bound. It's stable. On the right-hand side, we see that it's an unstable solution if the value of a is negative. And for this problem, a is negative 2. So now that gives me a positive exponent up here. So that thing's going to grow without bound. E to the 2t, as t grows in time, that value is going to eventually go to infinity. So it's going to grow without bound, and that's unstable. Now, in terms of airplane specifications, they're going to either specify a time constant or a time to double. Time constant is the value of time which makes the exponent minus 1. On a graph, it's going to be the time it takes to reach 63% of the steady state solution. And really, we only need the homogeneous solution to figure out what the time constant is. It's typically denoted with tau or capital T, and mathematically, it's simply just 1 divided by the value of A. On the unstable side, the time to double amplitude is the time difference from any one amplitude to double that amplitude. And again, it only comes from the homogeneous solution. It's typically denoted T sub D, and there's an equation for it, which is negative natural log of 2 divided by the value of A. And remember, A is a negative number, so that those two negatives will cancel to give you a positive time to double. But literally, if you have a plot, you can just grab any amplitude and then figure out the time difference to get to double that amplitude. And that's the same no matter where you start. Now we'll look at second order differential equations. Second order means you're going to need 2 boundary conditions to solve that. And you're going to get a stable solution when the damping ratio zeta is between 0 and positive 1. We're always going to assume the natural frequency is always positive. But the damping ratio is what we're going to focus on in terms of stability. In the example here, our damping ratio is positive 0.1. The natural frequency is 3. The damped frequency is going to be 2.985 for this example. But it's a stable solution. It's going to diminish over time. On the right-hand side of the chart, we see that if the damping ratio is negative, right, for this problem we have a negative 0.1 as a damping ratio. Even though it has the same natural frequency of 3 and the same damp frequency of 2.985, that damping ratio is going to make that signal grow without bound or become unstable. So when analyzing second order systems or second order differential equations, there's really 2 important characteristics. One is the frequency, and there's 2 versions of that we alluded to on the last slide. One is the damped frequency, often given omega sub d, and that's what we observe. And then there's the natural frequency, omega sub n, and that's what we would observe if there was 0 damping. The damping ratio zeta is a measure of the rate of convergence or divergence of the oscillation. Basically answers the question, does the amplitude shrink or grow over time? And again, these frequencies and damping come from our homogeneous solutions, so we don't need to worry about what the forcing functions are on the right-hand side of the equations. Again, we'll go through this example one more time to show you that we can get the natural frequency right from the equation. There it is. Our damped frequency is going to look at in the output there of 2.985, so that's what we're observing. And then the damping ratio, zeta, is coming right off the equation right there. So there's our example of damping ratio, damped frequency, and natural frequency, and we can get all of that on the plot as well. So next let's talk about solving these types of equations using Laplace transforms. Now a Laplace transform takes some function in time. So here's a function of time. Just take that and then shove it into this integral and then do the integration. And that gives you the Laplace transform. But you're going to end up with a new function that's not with respect to time, but is with respect to the Laplace variable s. And s in general is a complex number. So we lose all intuition of what the problem's doing. In time, we understand what a problem does in time because we know we can look at the time history and it makes sense. I don't know what s is. It's a complex number, and so I lose a little bit of intuition. But it's going to be a convenient way to solve differential equations. We do move from time to the frequency domain, but here's the thing. We now don't have to worry about differential equation. We get to use algebra, and everybody loves algebra. It's intuitive and we understand it. Differential equations, we have to go to the math department to get help. Our prerequisites for using Laplace transforms to solve the equations of motion, we really want linear differential equations with constant time invariant coefficients, and then we can use with or without a forcing function. That's not important at this point. Now we're engineers. We don't want to reinvent the wheel. The mathematicians have solved all these things over history, and so we just have to go find the Laplace transform table. Once we have that, we can go from time-based functions to Laplace-based functions and back and forth the other way. So here's all the common things that we would see in our model, our aircraft model, and this is whether it's in the Laplace variable s or the time variable t. I did highlight that in the Laplace table, most of these functions or most of these values have this e to the minus at. Some have e to the minus bt. That's going to be the driving force for stability analysis. We know that we want that to decay over time. We don't want it to grow without bound, and that just tells us that the value of a has to be a positive number, or the value of b in some of those cases has to be a positive number. So if we have a model where either a or b are negative, we know we're going to have an issue with stability because of that e to the minus at is going to grow without bound if those values are negative. So one of the convenient properties of Laplace transforms is that we can relate time-based derivatives to the Laplace variable just by using another s. So one derivative means you just multiply your function by s. If you have two derivatives, it's s squared. If you had a third derivative, it would be s cubed. Now this is very convenient, especially if the initial conditions are 0, because if they're not, you have some other baggage on the right-hand sides of those equations. But typically we start from trimmed flight because we're engineers and we're lazy, and it makes the math easy. So if we have 0 initial conditions by starting from trimmed flight, then we can basically use this property in our differential equations. So here's an example in the time domain where we have the time domain equation here. So we have two derivatives, one derivative, and so when we go to the frequency domain, we simply just replace every t in the equation with the Laplace variable s, and then if we have two derivatives, we have s squared. If we have one derivative, we just have s, and other than that, we just replace small letters with big letters. So x becomes capital X, little g becomes big G, and that's how you go from time domain to frequency domain, basically in one step, writing it down using that simple property of these derivatives. Many times it's convenient to put our models of our airplanes in a state space representation. So there's a state vector x, which contains all the output parameters. There's an input vector u, which contains the inputs. The A matrix contains the aircraft model values, and the B matrix contains how the airplane processes the inputs. So the state space model, whether it's in time domain or frequency domain, we can get the homogeneous solution. In the case of time domain, it's just x dot minus ax equals 0. In the case of the frequency domain, we have this si minus a times our state vector. We set that equal to 0, and that involves basically doing a determinant of si minus a, and that's solving that, setting that equal to 0 is what we call the characteristic equation. So next we'll start with our more simplified longitudinal equations of motion that we did before with some more assumptions, and basically just in one simple step write down the Laplace transform. And all that's going to be is every time we see derivatives, whether it's 1 or 2, it means we're just going to put s's or s squareds in front of the various parameters. And we do have some derivatives here. Here's a derivative of that, so we're going to have that s and so on. So it's not just the left-hand side of the equations. We have to meticulously look at the right-hand side as well and make sure we cover all the derivatives on the right-hand side as well with s's in front of those parameters. But in general, it's fairly easy to take three equations like we have here in time domain and then take the Laplace transform of those three equations and write that down. So then, now that we have the three longitudinal equations of motion, we've taken the Laplace transform, so now they're in the variable s. We should be able to write down a state space model of that. So our state vector, our output variables, would involve forward speed u, angle of attack alpha, and pitch attitude theta. And our input, our only input to the longitudinal equations, is the elevator deflection, delta E. So that's the input. And then the question comes, can we write this down in the state space model? And we could, except for the left-hand side is not quite s times the state variables. We have this s squared. So we're going to have to do an intermediate step, or basically add a fourth equation to help us get it and define a fourth state to help us get to the standard state space model. So I need to add a fourth state. In the time domain, it would be theta dot. Right, my state variables were forward speed, angle of attack, and pitch attitude. Now my fourth state is going to be the derivative of pitch attitude. So in Laplace, it's going to be s times theta, or delta theta. So that'll be my fourth state. So now I can take the derivative of that state vector, and now I can cover the s squared. But it's not going to be s squared. It's because the s is now buried inside the definition of the state variable. But now all of these have the right form with s times a state variable. So what that means is I had to add a fourth equation in my longitudinal set of equations, and it's just basically the identity equation. It just says that delta theta is going to be s times delta theta, and then it's the same thing on the right hand side, except for I put it in the curly brackets to denote that it is a state variable in and of itself. So, but it's still an identity equation, so it doesn't really change the value of anything in the dynamics. But now the form, I can then formulate the state space model in the standard form as shown, where A is given by the parameters here that I'm going to pull off of all these four equations above, just simply doing a good bit of accounting to make sure I know what's multiplying delta U, what's multiplying delta alpha, etc. I go line by line through that. That's going to give me the A matrix, and then I still have an input to the system, which is elevator deflection. So I have to go up there and find everywhere there's a delta E, figure out what's multiplying the elevator deflection, and make sure that's accounted for in the B matrix, or the B vector as shown here. So take all of these four equations and then put it in this matrix form down here with A and B as given by these two vectors and matrices. So for our stability analysis, we're going to focus on the homogeneous solution, and that shows the free response of the aircraft. In other words, how does the aircraft respond to any disturbance without any control forces? The free response shows the dynamic stability or instability of the system, but we're really going to get that by solving this characteristic equation of the determinant of S times the identity matrix minus A, our A matrix, and set that equal to 0. So from the previous slide, we noticed that we had the A matrix, but now we have S minus the A matrix, and you're only going to see S's on the main diagonal because that's S times the identity matrix. So that will put that S's on the main diagonal, and then the rest of the stuff is just coming off of minus A. So we're going to take the determinant of that and set that equal to 0. Ultimately, we're going to get a fourth order polynomial with these coefficients b1, b2, b3, and b4, and those will be determined by the specific values of these stability derivatives, xu, zu, etc., velocity, mu, and all these things are going to, once we do that determinant, we're going to have actual equations now to tell us what the b1, b2, b3, and b4 are. If you took control systems, a lot of times in the controls textbooks, they just give you those values as usually integers, and you don't know where they come from. But in this model, the B1, B2, etc., are going to come from the actual values of the stability derivatives, the velocities, the theta naughts, all the normal parameters of the aircraft are then going to go into what these actual values for these coefficients are. So it's a fourth order polynomial, which means we have three possibilities of how this thing's going to factor. We're either going to get 4 real roots, or we're going to get 2 real roots plus a complex conjugate pair, or we're going to get 2 complex pairs. So that's the three possibilities of how this fourth order polynomial will factor. And we're going to use the poles to determine the nature and stability of the individual modes of motion. So the poles are the values of S that make any of those roots 0. So we need to take the determinant of SI minus A. So let's just quickly refresh ourselves from math of how you take a determinant. If you have a 2x2 matrix, the determinant of that is just AD minus BC. In the case of a 3x3 matrix, a little more complex, you take A11 times its subdeterminant minus A12 times its subdeterminant plus A13 times its subdeterminant, and you can see what the value is there. And in our example, it's a 4x4 determinant, so it's going to be a little more complex, but in the end, you kind of can see how the determinants just scale. So you're going to have to know what 2x2 and 3x3 and ultimately solve those to figure out what the overall determinant of the 4x4 matrix is. So let's look at first order factors, second order factors, and let's figure out what the difference between a root and a factor is. So S plus A is the factor, and the root is the value of S, which makes that factor go to 0. In other words, S equals minus A is the root. Okay, and if that factor is in the denominator, we're going to call that a pole. If it's in the numerator, we'll call it a 0. But for now, let's just talk about factors and roots. In the second order system, we still want to find the values of S that make that 0, and we just use the quadratic formula to figure out what values of S. And there'll be 2 values of S that make that 0. And it's going to be a complex conjugate pair. The real part is sigma. The imaginary part is omega d, or the damped frequency, and we can relate natural frequency and damped frequency using the equation shown with the damping ratio. Now remember, on the Laplace table of Laplace transforms, we said that A had to be positive because we had all these e to the minus ATs floating around all over the table. So what that means is, for a positive A, it means that the pole, which is given a value of x, is going to be on the left half side of the complex plane. So the pole is going to be negative for a positive value of A. So in the case of a first order system, it's going to be stable. We have time constant, tau, it's 1 over A, and A is a positive number. If the pole falls in the right half plane for a negative value of A, then we're going to get a time to double because it's unstable. And remember, we have an equation, time to double is minus the natural log of 2 divided by A, where A is a negative number. In the case of the second order system, we get a complex conjugate pair, which means if we have 1 in the top half of the plane, we're going to have a mirror image on the bottom half of the plane. So they're going to come in complex pairs. But for stability, we need both of these complex poles to be in the left half plane. That's going to have a positive damping ratio. The natural frequency is the radial distance from the origin to the pole. The damp frequency is the y coordinate of the pole location. and then you can use some trig if you need to get that angle and relate that to the damping ratio. So in this example, we have 3 poles, one real pole and a complex conjugate pair. The complex conjugate pair is in the left half plane, so they're stable. And we said all it takes is to have one pole in the right half plane. You'll have an e to the minus at, but a is now negative, so that's going to be e to the positive number, which means that's going to be the dominating driver of stability and will ultimately drive the system unstable as time grows, because you have e to a positive number. Here's a stable example where all the poles are in the left half plane. Again, there's 3 poles, one real, and a complex conjugate pair. But in this case, the real pole is in the left half plane, and so the system will be overall stable. In the case of a pure second order system here with both poles in the left half plane, we can use our normal, we can first of all multiply those two together and get s squared plus 2 zeta omega ns plus omega n squared. Once we know that, we have equations for what sigma, the real part of s, is. It's minus zeta omega n, in this case minus 3. The damped frequency is 5, just coming off of the y component. The angle we can get to be 59 degrees, and once we have that angle, we'll use the cosine of that to figure out what the actual damping ratio is. In this case, 0.515. And then we can use the equation that relates damped frequency and the damping ratio to natural frequency, and just plug in the numbers above to get a natural frequency of 5.83 radians per second. And again, natural frequency is always the distance, radial distance from the origin to the pole. It's always going to be greater than or equal to the damped frequency, which is the y coordinate. So again, the hypotenuse of the triangle is always greater than or equal to any of the sides of the triangle. So omega n always greater than or equal to omega d. For the problem we just saw, we can then look at what the time output or the time history is. And we see that indeed it's got positive damping, 0.515. And we see that it damps out with minimal overshoots. And you can kind of get the frequency there, the natural frequency and the damped frequency as well. But it's positive, so it means it's a stable system. So just to recap, we're looking at dynamic system modes. We see there's typically first order modes that are impacting our static stability, but we're looking at the time constant or time to double, depending if it's stable or unstable. And then the second order modes is where we really can now analyze dynamic stability, and we're looking at frequency and damping, and the system dynamics are really just calculated from the homogeneous system, or really the poles of the characteristic equation. So that looked at using Laplace transforms to solve the equations of motion. The other thing you can do is start back from the original time-based equations of motion, and then use a MATLAB or some other differential equation solver to get you a numerical integration or numerical solution for the system of equations. So we can start with that, with our time-based equations, and not even deal with Laplace transforms. We still have to do our trick of adding the one identity equation for theta dot, because we really still need the left-hand side to be derivatives of all our state variables. So we'll add that fourth state variable, even though it's time domain. But that's what we need to use a function like MATLAB's ODE45. But again, that third equation that we add is just an identity equation, but it makes the overall system of equations then be able to be calculated. So we're going to solve this type of equation with some actual engineering numbers for now, these stability derivatives of xu, x alpha, etc. We'll put in, what we get out of the airplane model. And then now we have an actual system of equations that we could now input into MATLAB. So we've rewritten the same equations on the previous slide up here in the top in the blue box. And our goal now is to put it into the matrix form, or the state space form of the equations. And to do that, we just have to basically, again, meticulously go through each equation and write down the A matrix and the B vector that will result in the same model that we have in the blue box. So that's what's going on in the middle of the slide. It shows you the same set of equations but written in matrix form. And the neat thing about using a numerical integrator like MATLAB ODE45 is we're no longer restricted to 0 initial conditions. So when we did transfer function analysis, we put that restriction on. We said we're going to start from trimmed flight, make sure we have 0 initial conditions, because it made using the Laplace transforms easy. But in the case of numerical integration, we don't need that restriction at all. In fact, MATLAB will just ask you for what the initial conditions are. So you'll have to determine what those are. And in this case, you can see here that our initial delta forward speed is 0. That makes sense. So we're at least in unaccelerated flight. But we would probably have an initial angle of attack and maybe an initial pitch attitude. And for wings level, those are going to be the same. But we don't want any acceleration or rotation. So the delta theta dot term at initial conditions should be 0 as well. But the other two, at delta alpha and delta theta, would probably not be 0. And so we're able to start the numerical integration with non-zero initial conditions. So once we have a model ready to go, we would get on MATLAB and basically use the help function for ODE45. It's going to tell us the format of what that function is going to need. It's going to need an initial condition. It's going to need a time span. And then you're going to have to build a function file that has your basic model and your differential equations built in, but it's going to be of the form y prime is a function of time and y. And that's why we always have to have that identity equation in the case of ours, where we have derivatives of all our states on the left hand side of the equation, and then functions of those states and time on the right hand side. So for more information on that, if you just go to my YouTube channel, look for Brian Kish, and there should be a video on there on how to use ODE45 with an example and a model to help you walk through that. So now we'll talk about looking at airplanes in terms of transfer functions. We want to basically bring back in the input or the elevator deflection into the analysis, or the aileron or the rudder in the case of lateral direction. But we want to come up with and understand a model of how the airplane responds, or the output, based on a certain elevator deflection input. So a transfer function is going to be defined as the ratio of the output to the input of the system, and can be expressed in Laplace notation with 0 initial conditions as a ratio of polynomials in the Laplace variable s. So let's walk through an example. Here's a second order differential equation, x double dot plus 2 zeta omega n x dot plus omega n squared x. On the right hand side, we have a forcing function g of t. In line 2, we just apply the Laplace transform to that time-based equation, and we get s squared x of s plus 2 zeta omega n s x of s plus omega n squared x of s equals g of s. And so remember, going from time to Laplace, every time there's derivatives, you put s or powers of s, you change the small letters to capital letters, and you replace the variable t with the Laplace variable s. Now, going from the second to the third line is simply noticing that there's a capital X of s in each of the terms on the left-hand side, so we can just factor that out. And then we said that the transfer function is the output over the input, and so we just literally solve what is x divided by g, and in this case, it's 1 over s squared plus 2 zeta omega ns plus omega n squared. So that is the transfer function derived from the original differential equation. So once we have the transfer function, we're going to look at the denominator. The characteristic polynomial is going to be the denominator of the transfer function, and the characteristic equation is taking that polynomial and setting it to 0. Now let's discuss the difference between a single input, single output system versus a multiple input, multiple output system. So thus far we've really looked at the transfer function, which is an input, one input with a transfer function, one output. So we call that a SISO system. But we know that airplanes have multiple inputs, right? We have elevator, aileron, rudder, thrust, and we have multiple outputs. We have speeds, we have rotations, we have angles. So the airplane or aircraft are really multiple input, multiple output systems. So from a mathematical way of looking at a multiple input, multiple output system, let's start with a simple one which has two inputs or two forcing functions, f of t and g of t, and it has two output variables, x and y in this case, and the derivatives of the output variables, but really two output variables, x and y. We're looking for linear time invariant initial condition 0, and so this, even though it's two systems of equations and they're all coupled and linked, we still can do the Laplace transform of that entire system of equations just by the simple rules we've been following all along, where if we have derivatives, we use s and to the power that if there's two derivatives, s squared, etc. Again, small letters become capital letters, time becomes the Laplace variable s, and voila, we have the Laplace transform of a two-system set of equations. Now the question is, you can take that and put it in matrix form. We've done that as well, a state-space kind of a form, or just a matrix form of the equations. But then it begs the question, well, what are the transfer functions? In single input, single output, we only got one transfer function. Well, this is two inputs and two outputs. So basically, we can get the number of inputs times the number of outputs. That's how many transfer functions we can get when we look at this math model. So then the next step is, well, what are the different transfer functions? We have x over f, y over f, x over g, y over g. So how do you get those from the model we have, mathematical model in matrix form in front of us? So Kramers Rule, something we learned in high school, but basically we're going to use good old-fashioned Kramers Rule to break out whatever transfer function we need, whether that's y to g or x to f or whatever. We can use Kramers Rule to figure that out. Let's first look at if we want the transfer function x over f. So we'll solve for vector in row 1. It's in red. Take the determinant of a matrix with column 1 replaced by vector f. That's in the numerator determinant. The denominator determinant is the original matrix on the left-hand side of the equation. So for this example, you can see how we substitute 1, 0 for column 1 in the numerator determinant, and that's going to give us, if we want the transfer function x to f. If we want y to f, then we have to solve for vector row 2. In this case, our numerator determinant is going to replace column 2 with the vector f, or 1, 0. So that's how you're going to sort out, depending on which transfer function you need, you're going to apply Kramers Rule. I just gave you an example of 2. We could also apply Kramers Rule if we wanted x to g or y to g with slight variations of what you've seen here, but it's the same basic idea. So now let's walk through an example with actual numbers as opposed to just generic A, B, C, and D matrices. Now we've got actual polynomials in these matrices. So we want to determine what the transfer function x to f is. So again, we put 1, 0 in that column. We grab the s squared plus 3, s squared plus 2 in that column. And then the denominator is the determinant of the entire matrix on the left-hand side of the equation. When we do, if we need the y to f transfer function, again, just put that in the second column. That goes in the first column. And you would take the determinants to figure out what that is. So here's one where we're going to walk through the actual determinants. We set it up x to f. We see the determinants there. Now we actually have to solve for the determinants. In the numerator, it results in s squared plus 2. The determinant of the denominator, a little more complicated, but kind of cleans up nicely to s to the 4th minus 1. And in the end, that's the transfer function, the ratio of polynomials of output to input. When we want to know what the roots are, well, we have some roots in the numerator. Those are called zeros. So we just find the values of s that result in the numerator going to 0. And in this case, it's plus or minus the square root of 2 times j, which is the square root of -1, an imaginary number. And then in the case of the denominator, we get, it's a 4th order. So we have plus or minus j, and then plus or minus 1 are the values of s, which make the denominator go to 0. And we call those poles. So let's go back to our complex plane and our root plots. And really, stability comes down to what's going on in the denominator or the poles. In this case, sure, we have a 0 at s equals -1. It's in the left half plane, but it doesn't really impact stability. What's really making the system go unstable is that one pole in the denominator of s equals plus 1. One pole in the denominator makes the system unstable. Now, we can use control theory or control inputs to basically cancel out if we have an unstable pole in the right half plane. We could in essence mathematically cancel that pole by putting the same thing, a 0, at the same location, and mathematically they would cancel. So sometimes we can use control input to eliminate an unstable pole. All right, back to our more simplified longitudinal equations of motion. So we have them. Here's the 4 equations. We added the identity equation, and it's already got the Laplace transform has been applied. We want to put that in our standard state space notation. And to do that, we know that our state is defined as the u, alpha, theta, and then the derivative of theta, or s times theta. Our input to the system in the longitudinal case is the elevator deflection, and our A matrix and B vector have been defined as previously on the other slides. So that's kind of a review. Next, we want to solve the equation as shown here. So we need to know what SI minus A is. So that's basically just putting the S times the identity matrix, subtracting the A matrix. We did that before. This is SI minus A. The state vector is the same. The control vector is the same. The B is the same. So that's the step for there. But we want to eventually get to a transfer function. So this sets that up. But now we could have any number of transfer functions. We could have a transfer function of u to delta E, alpha to delta E, theta to delta E, or s theta to delta E. For this example, on this slide, we really want the transfer function of pitch attitude as a result of elevator deflection. So delta theta over delta delta E. To get that, we have to apply Kramers Rule. And so what I've shown here is how we want to solve for, since delta theta is the third state variable, we have to replace the third column with basically the B matrix. So the green column there is what the B matrix is. That replaces the third column in the numerator determinant. And then, so now we've got the transfer function ready to go. We just have to solve now 2 4x4 determinants and with a lot of algebra. But ultimately, we're going to get this form of a transfer function. It's going to have an overall constant k, or a gain, and it's going to have a numerator polynomial with an a1 and an a2 coefficient. It'll be a second order polynomial in the numerator, and then the denominator will be a fourth order polynomial with b1, b2, b3, and b4 coefficients. And keeping everything in terms of generic variables from those determinants on the previous slide, we can solve that and come up with nice equations that are independent of which aircraft model we have. And it'll always be this form of an equation, a second order polynomial or a fourth order polynomial, depending on whether it's a Cessna, a Boeing 747, or whatever. We just once we have these general equations, we then will substitute in the specific stability and control derivatives and velocities and other information, and be able to solve or get the transfer function of theta to delta E for that specific aircraft. So this slide shows you the generic formulas for everything in the numerator plus the k. Now, on the next slide, I'll show you what the generic formulas are for the b coefficients in the denominator. So this is how, again, now that we have these written down in generic form, then we could apply specific examples from a specific aircraft and actually get the transfer function. So let's do that. So here's an F-16. In this case, all the stability and control derivatives were given in terms of non-dimensional derivatives, so we'll have to scale those back the other way because our equations on the previous two slides assume that we had dimensional stability and control derivatives. So you'll have to review the slides from previous weeks to understand how we go from dimensional derivatives to non-dimensional derivatives. But in the end, it shouldn't matter. You should be able to take data from any aircraft, whatever form it's given, and then manipulate it to the form of the equations you need. So for this example of the F-16, it gives us our flight condition, our trim condition, so our speed, dynamic pressure, initial angle of attack, and pitch attitude. It gives us the stability and control derivatives for the F-16 at that given flight condition, so at a certain altitude and speed or Mach number. And then we also have the aircraft properties, terms of wing area, chord, wingspan, all that stuff, mass. That's always going to be provided as well. And if you take all that data for the F-16 and then manipulate it into dimensional stability and control derivatives and use the equations on the previous two slides, when all the smoke clears, you're going to have your A1, your A2, and your B1, B2, B3, and B4, and your K are going to come from those properties, and you'll end up with one transfer function, pitch attitude for elevator deflection for the F-16. So for this lecture and solving the equations of motion, we use the longitudinal equations to walk through the different ways of solving it with analytic differential equations versus Laplace transform versus numerical integration. We can basically apply the same exact tools or techniques to the lateral directional equations and end up with a similar type of result where we have transfer functions. In this case, it would be, say, roll angle to aileron deflection or some other transfer function, depending on what we need. But the techniques are the same, and so we're not going to walk through in another 30 or 40 slides of how you handle the lateral directional equations of motion. We'll probably just save that for a homework assignment to give you guys practice using the slides here and how the techniques we apply to longitudinal, but we'll have you guys practice the same techniques and see if you understand how to pull out the specific transfer function you need given all the variables that are provided. With that, this concludes the module on solving the equations of motion.